P doesn't mean anything else, does it? No. That's equal to mg h plus x. Or we can simply just write that w plus h. Okay, and x is the change in length of the bar. We would normally call that delta L. And we know from previous work that that's equal to sigma over E. So that's the strain times L. Okay. So I can substitute that in and I get the potential energy is equal to W times sigma over E times L plus, well, WH. So therefore, we can write that the strain energy is equal to P. So sigma squared over 2E times the volume, which is the area times the length. So this is only really good for bars which have that formula for their length. That's all equal to, just rearrange that a little bit. Okay, we get that. So if we rearrange that, we get a quadratic equation. So I'll just get rid of that for a minute. So we get, sorry, that should be AL over 2E. We'll just get rid of that. So AL over 2E times sigma squared minus WL over E times sigma minus WH equals 0. Okay, so it's a quadratic equation in F. And if you remember your solution for a quadratic equation, if you have an equation ax squared plus bx plus c equals 0, x is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, so that's the kind of a general solution. And we can do the same thing here. So to solve for stress, coefficient of sigma squared is L over 2E. Coefficient of sigma is minus WL over E. And the C part would be minus WH. Okay. So you can solve that equation for stress, and you'll get two answers. Okay, so the question is, well, what does that mean if there's two answers? Well, the answer is, let's look at what these bits are. So we take the, say, x equals minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. Let's look at this bit first. So that bit is well, the b part is WL over E, so it's minus WL over E divided by 2A that's equal to, well, the minus goes, and that's equal to 2E over AL. Well, that 2 goes with that one, so that goes there, times WL over E. So that is, if we cancel everything there, so we can cancel those, so that's equal to W over A. Okay, so that's the static part of the stress. which is force over area. Okay, so that part is a static stress, and the other part is the dynamic part of the stress. Okay, so another color. Okay, so this part is the dynamic part. Okay, so if you imagine what happens if you have a pillar or a post or something like that, and you have a mass that drops onto it. If you plot let's suppose you plot the change in length of the shaft against time, what you would get would be something like that. Okay? And if you left it long enough, it would die away. So actually, this part here would be W over A. Okay, and this part here would be the dynamic part. So the plus and minus values you're getting are the value here and the value here. Okay, so that's why you have two values. So what happens is, if you drop the thing, yeah, derivative A is the area. If you drop the thing onto the pole, it'll oscillate. It'll vibrate up and down. Okay, now eventually that vibration will dissipate and you're left with just a static displacement. But in the meantime, you've had all these higher stresses. Okay, so that's what happens. Okay, so that's why you get two values, and one of them is probably well, one is plus and one is minus. So one is tension, one is compression. So you get this thing where they oscillate up and down. Okay, so that's just a comment. We did an example already, and we'll do another one. Now I want to just take another look at this equation today. There's in the homework exercise there is an exercise where you have to work out the equations for stress and find the maximum stress for something dropped from different heights. But if you look at old exam questions, let's just write this equation out again. So it was AL over 2E times stress squared minus WL over E times stress minus WH equals 0. And if you look at old exam questions, solving for stress in an exam is quite difficult because it's solving a quadratic equation, and B, these numbers tend to be very large or very small no matter what units you use. Okay, because I mean, stress squared, if you're using pascals, it's 10 to the 12, and this is 10 to the minus 18 and stuff, so 10 to the minus 9. So the numbers are awkward, and it's a difficult thing to do. So if you look at old questions, okay, they're formulated as solve for L, A, or H, not stress, and this is just due to difficulty. Situation. Okay, we'll take a look at one of those just for completeness. And then we'll just come back at the end. We'll just come back and talk about that formula again because you're going to need to use that in your exercise. Okay, so let's get one of these things. Okay, where are we? January 2019. So this is question number 1. Just see if we can lower this down here a bit. There we go. Okay, so question number 1, part A says, define strain energy and describe briefly how it's used in the analysis of impact stress. And then question part B is, there's a vertical steel column is to be compressed by a mass of 200 kilos falling from a height of 120 millimeters. The column of steel is 200 millimeters in diameter. Find the minimum length of the column if the allowable stress is not to exceed 100 megapascals. So we'll talk about that in a second. Just to look at part A for a minute. Strain energy is the energy stored, it's potential energy stored in an elastic body due to strain or deformation or elastic deformation, if you whatever way you want to put it. So we'll just take a look at this. So 2019 strain energy is the potential energy stored elastic body due to elastic deformation, and you could give a numerical definition there. So U is equal to sigma squared over 2E times the volume for a body with uniform stress. All right, so that's a definition. Now, how is it used to analyze stress, impact stresses? Well, the assumption that all kinetic energy of the impacting body is absorbed elastically by the, I suppose, the impacted body as strain energy. Okay, it's a very kind of, it's assuming a lot actually, because I mean, if you have two, let's suppose you have two steel ball bearings. I don't know, when we were kids, we used to use these big ball bearings for marbles, and if you had two of those that hit each other, which one is the impacting body and which one is the impacted one? So they're both going to absorb some energy. Okay, so it's not exactly what happens. Okay, but it is a it is a worst case scenario. Okay, I suppose. So it's an approximate guide. Okay, so what you're saying is, you know, I mean, when those two bodies collide, the energy will go anywhere. You can get little chips broken off, or you can get local dents in it, which is not elastic, it's plastic. You can have noise, you can have vibration, you can have all sorts of things. But this is a general assumption. So it's more here to illustrate the point that dynamic loading can be much more severe than static loading, than it is actually to give an accurate description. There are other ways that you can do this, which are much more complex. Okay, so that's part A. So let's have a look at part B again. So it says, sorry, let's pull it up a bit. A vertical cylindrical column is to be compressed by a mass of 200 kilos falling from a height of 120 millimeters. The column is of steel, 200 mils in diameter. Okay, so that's and we're solving for, yeah, the length of the column, isn't it? Yeah. So let's just do a little sketch as always. Excuse me. So we have this steel column. We know the diameter. We have this mass, which is falling from a height of 120 millimeters, and it's 200 kilograms. Okay, and then the cylinder has a height of L. Okay, H is used for the height the falling height. So that's usually h. So the length of the cylinder is L. So it's solid steel. E is 200 gigapascals. Okay. So we'll write out our equation and see what we need. This it's always the way to approach these. So we have AL over 2 times sigma squared minus WL over E times sigma minus WH equals 0. So what do we know? We know the stress because we're told the maximum stress that's allowable is 100 megapascals. Okay, we can work out the area. We know what E is. We can work out W. We know what H is. So we know everything except L. So we're solving for L. So the thing to do is to rearrange the equation so that we have something in terms of L. So if I do that, L features there and it features there. So I can take it out. So I can say A sigma squared over 2E minus W sigma over E times L. I can bring that back over to the other side equals WH. Okay, and I can work out those numbers inside there. Okay, so yeah, so that's all I need to do is start plugging in numbers there. So and we just need A. So A is equal to pi over 4 times 200 squared, which is pi times 100 squared, which is 10,000 pi, which is 31416 square millimeters. So so we can start plugging the numbers in here. So we can say 31416 times sigma is 100 squared divided by E is 200,000 newtons per millimeter squared. So that by 2 is 400,000. Minus, okay, W is the weight, okay? And the weight is mg, so we'll just put 200 by 9.81. And that works out as 1962. Yes, 1962. It's not the mass, but it's the weight. Right. So that minus, so 1962 times the height, which is 120 millimeters, divided by E, which is that. Okay. And that times L is equal to, sorry, that should be 100 back there, which is stress. And this is the W times the height. All right. So if you work all that out, we won't make you do it, but if you do work it out, it comes, I think, to 785.375 minus 0.981 times L, and that's equal to 235,440. Okay. So if you work out, if you divide one by the other, you end up with L is equal to 235,440 divided by whatever that is, 785.75 minus 9.981, and that actually comes out to 300 millimeters. Okay, so the column, to keep the stress below 100 megapascals, column must be 300 millimeters height. Or greater. Okay, if the column was twice as high, we'd be storing the same. So the amount of energy from the block is the same. So if the column was twice as high, we can store the same amount of energy in double the volume. So the strain energy in any given part of the thing is higher. Okay, so as the column becomes smaller, sorry, the strain energy is the same, but the stress required to get that is higher because the volume is going down. So the taller the column, the lower the maximum stress. Okay, so okay, and if you work those out, you find that they tend to be much, the dynamic stress tends to be much higher. You'll see that when you do the exercise. The dynamic stress tends to be much, much higher than the static stress, unless it's just dropped from a little tiny distance. Okay, so there's another example there from 2014. I think I'll just leave that. I'll put up a little video of that solution, and you can work on that. Okay, but the basic principle here is that something which is loaded dynamically will suffer a much higher level of stress than loaded statically, particularly if it's a mass falling on the thing. And we did have these three cases before, so we said there were three cases. Case one was the mass was gently lowered onto whatever it is, the post or the column. Okay, and in that case, the maximum stress is just the weight divided by the cross-sectional area, as you'd expect. Okay. The second case is that the mass is suddenly applied. So in other words, it's dropped from 0. Okay, and we worked out that formula before. Basically, if we look at that formula again, we have, so we would have AL over 2E times sigma squared minus WL over E times sigma minus WH equals 0. So what would happen there is H is 0. So just get AL over 2E times sigma squared, WL over E times sigma. Cancel a few things there. So so we get A over 2 times sigma is equal to W. So sigma is equal to twice W. So it's twice the static load. Okay, so imagine if you want to, if you want to visualize that, let's suppose you were, I don't know, there were two of you and you were lifting a heavy table or something and you're going to carry it from one side of the room to the other. If you lift it up and you kind of lower it gently down onto the ground and just let the ground take the weight slowly and feel the weight ease off slowly, that's case one. Case two would be you bring it across, you can barely lift it, it's just hovering over the ground. You bring it across and then you let it go. And it doesn't actually fall, but the weight is suddenly. And of course, what happens, well, okay, yeah, we'll talk about it in a sec. So the third case then is drop from a height. So the stress is the solution of that. Okay, and it's usually much higher than the static. And I think that's the point. I think if you go from a load, if you just say, oh, there's a force, there's a weight acting on that, it's well, the force is mg, and then the stress is that divided by area. That's fine, but how did the weight get there is the question. So if it was gently lowered into place, then what would happen is the column would slowly begin to take up more and more of the weight, and the most you'd ever see would be that. In case number 2, when the mass is suddenly applied but not dropped, surprisingly, it's higher. And in the third case, it's much higher. So we'll just draw a graph there, maybe. So we'll call that the stress, and we'll call that time. And so the static case would be no, I won't go that far up. That's case 1. The dynamic case, so that's W over A. The dynamic case is the suddenly applied one would be something like that. Okay, so the peak stress would be twice the static load, and the lowest stress would be 0. Okay. And then the third case, where it's dropped from a height, would look something like that. Okay, where this is greater than W over A, and this would be tension. Okay, so that's what happens. So if you come out of this knowing that, you know, a load that's applied dynamically has the potential to cause a much higher stress than the load applied statically, then that's really what you're after. Okay, so in the case of the example in the homework, you're basically asked to solve that quadratic equation for stress. Okay, so you've got this plus that. Just writing it that way just to emphasize A, B, and C equals 0. So the solution will be minus B over 2A plus or minus square root of squared minus 4 times that times that divided by 2AL over 2E. Okay, so that's what you get. So you can work those out. You can simplify those equations quite a bit. So that would actually simplify down to first bit The 2 goes, so it's W over A. Plus or minus. You can't do much more with that, I don't think. So you probably leave that as it was. So the minus sign will disappear because of the squaring, and this minus sign will disappear as well. So A divided by L over E. Yeah, that's about, yeah, I mean, you have to just work that out. So what you do is you put that into a spreadsheet, that formula into a spreadsheet, and it will produce 2 values, static plus dynamic, which will be compressive, and static, which might be tensile. And what you'll find is that if you drop the block from anything more than a very, very small height, or even any time at all, the dynamic stress would be much bigger. And when you do these exam questions, if you look at them, which you don't really need to do, the static bit is always really small compared to the dynamic bit. So that's the main. That is the main point. Okay, and so what you've got here, you're not going to get some kind of a question on that, I don't think, in the multiple choice or the final assessment. But there is an exercise in the spreadsheet exercise to do that, so that'll give you some idea of what's going on. Okay, so I think that's as much as I might. So I might throw up a little video just to reinforce these, but that's really as much as we need. So that's kind of the course. So I suppose we can think about revision. Now, revision, I mean, you have just done and you're just launching into some coursework based on bending and I values and sections like that and torsion. So that stuff should be fairly fresh. And you know, you've done the eccentric loading recently. So what we'll do for the next couple of lectures is, what I'll do is I'll talk to you tomorrow about the shape of the last assessment, because it's not, I mean, you can't ask the entire thing in a shorter scale assessment. So I'll have a look and see what happened today, and I'll go through some topics that maybe need to be revised, and I'll just explain what the shape of it is. Okay, so that's really it. I mean, I know I have to mark the previous homework, so I'll do that next. That's my next job. The assessment that you're doing at the moment will mark itself. So we'll just say, so the weekend assessment, if you want to put it that way. It'll self mark. And it'll give you 1 point per question, as far as I know. What you see there is not the final answer. So the final grade is based on the answers plus the hand calculations. Okay, and said beforehand in the email, no hand calculations means no grade. But the point about this is, you'll get a 1 or a 0. If you look at the actual grade, you'll get a 1 or a 0 depending on whether the answer is right or not. But I'll be giving 5 marks per question, and some of that goes for the answers and some of it goes for the hand calculation. So if you do the right approach but you get the wrong answer, you'll still get marks, which is as it would be normally. So So if you see something in a column in the gradebook, it might just be a mark out of 4. It'll probably just be a percentage and a mark out of 4. That tells you how many questions you got right, but it's not the whole story as far as your answers are concerned. So just be aware of that. And yeah, that's basically it. I think that's how the last one will work as well during the exams, because I like the idea of getting the answers in a fixed time, and then the other stuff coming in later. So, okay, so we'll leave it there. Solutions to the quiz questions during the week. Yeah, I will. I certainly will. Yeah, I'll put up solutions to everything actually during the week. And what I would suggest is don't hand up the second homework until you get some sight of the results of the first homework. So yeah, I'll do those, and we'll see where that goes. Okay, so are there any questions? Second homework, I put a date of the 4th of January on that. I don't know how you're fixed in terms of, you guys don't normally have too many written exams in semester 1, so I'm not pushed about that. It needs to be in so that I can mark it before we have to have your results in. You start exams on the 5th. Okay. Yeah, I mean, it doesn't have to be done before my exam or anything like that. So I don't really, as long as I can get it and mark it before I have to have the results in, which is probably going to be sometime around the end of January. I don't mind doing that. So I'm flexible on that date. I mean, if the class rep wants to have a discussion with the class, you can move it. I don't know what your workload is like over the next week or two, but I'm kind of flexible on that. I've just kind of picked it, just so you had it done before the exams. But as I say, I'm not pushed as to when it's done. So you guys can have a think about that. Okay, so yeah, I'll take a look at that later on tonight, and I'll make a decision on what will just where to point you in terms of revision and stuff. There's quite a bit of video content up on the module already. I'll put some more up, but we'll see how that goes. And just looks like we'll be doing the same thing for semester 2, unless there's a radical change. So I would expect it to work out roughly similar to this module. I'll probably run the assessments in a similar manner, but I'll give you a proper schedule, okay, this time around, because I'll know how it's going to work. And just for the record, usually the Applied Mechanics 2 module is a bit easier than the Applied Mechanics 1. The subject is a bit easier to handle. So, and just again to clarify, a lot of people get this confused. Applied Mechanics 1 is over and done with after the exams. Applied Mechanics 2 is a completely different module. There's no carryover. So whatever you get in January, that's it, and then we move on to a new module. Okay. So I think I'm going to leave it there. I think it's important to be in the class tomorrow because on Wednesday, because I'll have a few words to say about what's coming up, and how to prepare for it. So if that's it, if there's nothing else, I'll let people go. Okay, so I'll see you tomorrow.
You are currently the only person in this conference.